Welcome for the session. So in the previous classes we have discussed mathematical modeling of physical systems. In that, mechanical system, electrical system, electromechanical system, hydraulic system, pneumatic system and thermal system. These things we have derived an expression and that mathematical model is obtained. In that, the final thing what we have derived is the Laplace transformation of output variable to the Laplace transformation of input variable under the initial condition 0. So this is a mathematical model we have obtained for a different systems. After obtaining mathematical model, what we have to do is we have used several techniques in order to obtain a mathematical model. One is an analytical method, another one is block diagram reduction technique, and another one is signal flow graph. So these are the different methods to obtain a mathematical model. In other words, we will call it as transfer function. The transfer function what we have obtained in the cases is nothing but closed loop transfer function, which is nothing but C of s divided by R of s will be equal to G of s divided by 1 plus G of s into H of s. This is a thing what we have derived in the previous classes. Now let us start how to analyze a mathematical model in detail. So this part onwards, module 3 onwards, you have an analysis part. Here we are going to analyze with respect to time and with respect to frequency. If you analyze control variable with respect to time, it is nothing but time response analysis. If you analyze controlled output variable with respect to frequency is frequency response analysis. There are two things in control system analysis. One is time response analysis and another one is frequency response analysis. And each response will have a several weightage. Some of the times time response analysis will be easier, some of the times frequency response analysis will be easier. Whenever we deal with time response analysis, here we will consider time domain specification. Whenever we analyze frequency response analysis, we will consider frequency domain specifications. Let us see what exactly is a time response. The controlled output variable will depends upon certain parameters and each parameters will play a certain role on stability. Whenever if the parameter is wrong, then it affects the stability. If parameter is correct, then stability will not get affected. Like this, there are several specifications, we will call it as system performance parameters, which affects the stability of a control systems. Sometimes accuracy is also an important when we ascertain the stability of the system. If the stability is achieved, then the next thing is accuracy. In the accuracy, the time parameter will play a major role. Whenever we analyze accuracy as a parameter, then time parameters, time response will play a vital role. Response time, settling time, etc. These parameters will come into a picture. Let us see a control system is having a response curve like this. Initially, it is having the response like this, it is having a higher amplitude, then the amplitude will get decayed to a 0. After that, the output will be maintained in a stable fashion. In the first successive cycles, the amplitude is varying with respect to time continuously. This part is nothing but it is transient response. Here the output, controlled output variables, what we will call it as C of t, will be varying with respect to time continuously. After that, we need to maintain the output to a certain value that we will call it as steady state response. So when I take up an overall response of the system C of t, it will be consisting of transient response and steady state response. So this is an expression for overall response of a system. Sometimes directly we will write transient response in terms of C of t, but steady state response will be represented as steady state error. So this is the overall response of the system, which consists of transient part where the controlled output variable will be varying continuously with respect to time. Steady state output is one. The controlled variable will not vary with respect to time. Here we will get the stable part. Whenever we take up a transient response, this cycle is very important. Up to this, the time taken to settle, time taken to obtain the stable output, that is called as settling time. In practical systems, the settling time should be very minimum. That means within a span of time, it should achieve the stable output. In some of the times when you switch on the CPU, you will be experiencing the OS will be getting rebooted. After some time, the screen will be appearing steadily. So initially the booting of the software and booting of the applications what you are using in Windows, that is continuously varying. It is like a transient response, and after some time you will be obtaining a desktop screen, and that will be a constant. That is nothing but steady state response. So in all the control systems, we need to take care about what is the transient part and what is the steady state part. Both the cases, it is very important. Whenever we take up a transient response, the amplitude should not vary much. We have to give a suitable damping in order to obtain a stable output. After that, after obtaining the stable output, we need to maintain it. The maintenance of stable output is very important. That is taken care by steady state response. And the response curve will be different for different types of signals. Let us see what are the different types of test signals we will be using in control systems. I will call it as standard test signals, or in other words, different types of inputs. That is also name for this. Number one, the easiest one is step input. Again, there are several types of test signals. It can be a square form, it can be a triangular form, it can be a circle, and it can be a step input, it can be a ramp input, it can be a parabolic input, it can be an impulse input. But basically, they have segregated as a standard type of signals. So these segregation, if the control systems is giving output for these signals, then we will say it will be giving for all the types of signals. So the standard test signals are classified based on some designations. The first one is step input, second one is ramp input, and number 3, it is parabolic input, and number 4, impulse input. Most of the cases we will not consider the impulse input because impulse input is one of the derivative of step input. Hence, for analysis purpose, impulse input will not take into a consideration. Only we will test for step input, ramp input, and parabolic input. Let us see what are the characteristic features of each input signal. First, I will take step input signal. I will take A as an amplitude of signal. It is A, or it is nothing but it is gain. I will take A as a gain. Let us consider the step input signal. As the name itself indicates, it is step. That means the signal is changing from lower intensity to higher intensity level. So this is nothing but a step signals. It is changing from lower level to higher level. It is stepping up. So this is time 0. Sometimes C of t is represented as a controlled output signal. For the specific purpose, what I will do is, I will be using R of t. R of t is the reference input signal. If you just recall a block diagram, the block diagram consists of R of t. The transfer function in the forward path is G of s. Then C of t is the controlled output signal. Then H of s is the block. It is a transfer function in the feedback path. Then the signal which is getting from feedback is feedback signal B of s. And signal we are fetching to G of s is error signal, which is the comparison signal of reference input and feedback signal. Generally, everything will be expressed in terms of S or in terms of T. So I will try to express everything in terms of T only. And finally, that will be converted to S. So R of t here is reference input signal. This is a step output. It is having a gain A. The condition for step signal is if R of t will be equal to A when t is greater than 0, otherwise it is 0. So the reference input signal exists whenever the time should be greater than 0. Not equal to 0 is also not possible. That should be greater than 0. It should have some limits. We are obtaining the expression in terms of t domain, and that will be converted to S domain. If I convert R of t to R of S, then we will be using Laplace transformation for converting this. Before that, if I make A is equal to 1, A is equal to 1 indicates it is unit step signal. Sometimes that is also possible. If I make A is equal to 1, you will get unit inputs. If it is A is equal to 1 for step input, it is unit step input. If A is equal to 1 for ramp input, unit ramp input. If A is equal to 1 for parabolic input, it is unit parabolic input. That is a designation what we will be taking. So let us convert t domain to S domain. For that I need to apply Laplace transformation. If I apply Laplace transformation, if I recall the result, Laplace of 1 will be equal to 1 by S. So A is a constant, so R of S will be equal to, t domain will be converted to S domain, and A will be A of S. This is a reference input signal in t domain and reference input signal in S domain for the step input signal. Next, second one, ramp input. Again, ramp is nothing but it is going 0 to some linear graph. So what I will do is, again this is R of t, this is time, this is 0, and this is ramp input. Again there will be a gain. It is varies linearly. This is 0 to some level. This is varying linearly. Again I will recall R of t for ramp input. It will be equal to A into t if t is greater than 0, 0 if t is less than 0. Again, basic line equation y is equal to mx plus c. Here we are not considering c, just mx. It is just like mt. Here where m is a constant, here we have taken that as a gain. Again, if I apply Laplace transformation for this, what happens? R of t changes to R of s and A of t. Let us recall what is Laplace of t to the power of n. Laplace of t to the power of n is nothing but gamma of n plus 1 divided by s to the power of n plus 1. If n is a fraction, also there is another formula. If n is an integer, Laplace of t to the power of n will be given by n factorial divided by s to the power of n plus 1 if n is an integer. So here n is an integer, we will call it as the power of t is 1. Since the power of t is 1, the Laplace transformation will be t to the power of n. T to the power of n will be 1 factorial divided by s to the power of 1 plus 1. This is a Laplace transformation for t to the power of 1. So if you substitute, it will be a divided by s square. This is the reference input signal in s domain for ramp input. Next, number 3, parabolic input. Parabolic input is 1. The output varies with respect to time parabolically. So the curve for this is parabola. So here the variation of output with respect to input is parabolically variations. Again, the reference input signal for parabola input will be equal to r of t will be equal to a t square by 2 when t is greater than 0, otherwise 0 if t is less than 0. Again, apply Laplace transformation. What you will get? If you apply Laplace transformation, r of s will be equal to a is constant, take out Laplace of t square by 2. What is Laplace of t square by 2? Just Laplace of t square will be 2 factorial divided by s to the power of 2 plus 1. So s to the power of 3. If I substitute this here, this is a by 2, I will take out common. What is the Laplace transformation of t square? 2 factorial is 2 into 1 divided by s cube. So 2 will get cancels, you will get a divided by s cube. So we will be representing the signal in terms of time domain as well as s domain. So this is very important for these 3 inputs. Let us take the block diagram analysis. So steady state analysis for general block diagram of a control system. We will take a simple closed loop control system and we will be analyzing what is the steady state output. Here the name steady state indicates what is steady state. Steady state means the output will not varies with respect to time after the transient state. That means initially the amplitude of the signal is varies with respect to time. After that the output will be stable and that stable output will not varies with respect to time. That point is called as steady state output. I will consider a simple closed loop control system which is having one forward path transfer function, one feedback path transfer function and one input and one output. So I will be considering input as r of t and g of s is the transfer function in the forward path. Then r of s I will take as a reference input signal. I will be taking capital R of s. You can take even r of t also, no problem. C of s controlled output signal, then a takeoff point. H of s is a feedback signal and this is a simple closed loop control system block diagram. Also there are other signals. One is E of s, it is nothing but error signal. It is a comparison of a reference input signal and feedback signal B of S. So let R of S is reference input signal, B of S is feedback signal, C of S is controlled output signal, and E of S is error signal. G of S is the transfer function in the forward path, which is given by output by input. What is the output? C of S, and input is E of S. This is a transfer function in the forward path. Also, H of S is the transfer function in feedback path. Again, output is B of S and input is C of S. So this is transfer function in forward path, and this is transfer function in feedback path. So these things you have studied in the previous sessions in the block diagram algebra. My intention is to obtain what is the steady state output. We know that E of S will be, what is E of S? E of S is nothing but error signal. It is a difference between reference input signal minus feedback signal. If I take, it is a negative feedback. So this is a negative feedback system. What is R of S? Keep as it is. What is B of S? B of S can be replaced with C of S into H of S using this definition. Then R of S will be retained. What is C of S? C of S can be replaced with G of S into E of S. So it will be E of S into G of S into H of S. This is E of S. If I take this here, E of S plus E of S into G of S into H of S will be equal to R of S. Here I will be taking out error signal as a common, E of S as a common, and 1 plus G of S into H of S, that is equal to R of S. Then what is E of S? Error signal E of S will be equal to R of S divided by 1 plus G of S into H of S. This is what error signal is, depends upon the reference input signal and open loop transfer function. Whenever we analyze a steady state output, two parameters are very important. One is settling time. Settling time is a time in which the output reaches to a steady state. That means whenever you will get a stable output, that time is nothing but it is the settling time. Then another important thing is, what is the error in the system? What is the error in the system? So these two things we will be analyzing whenever we take steady state output. These are the different two parameters what we'll be analyzing. Settling time, it will be calculated based on time domain specification. But what is this error? This error is nothing but E of S. Here, this error directly we will not give E of S. We will be calculating what is the error at 0 and error at infinity. So this error is calculated in terms of an interval, because we need to maintain the stable output up to certain amount of time. We don't know. Up to infinity, yeah, it might be there. That's why we need to study what is the variation of error from 0 to infinite. So that's why this E of S is taken under the limit that will be steady state error. Whenever we study steady state error, the steady state error depends upon One parameter is reference input signal and another one is open loop transfer function. These two are the parameters in which the steady state error depends. What is this ESS? Steady state error will be equal to limit of limit of t tends to infinity E of S. This is the total steady state error in the system. Then when we use final value theorem, steady state error will be equal to, I will be substituting this to certain limit, so S into limit of t tends to 0. So don't write S here directly because S is also variable. So S into E of S. This is what we will be calculating the steady state error for a different input signals. This is an important expression for steady state error. Also remember another thing is, what is E of S for a closed loop transfer function? E of S is this. Steady state error will be equal to limit of t tends to 0 S into R of S divided by 1 plus G of S into H of S. While writing limits, you have to be caution. Whenever you use capital L, it should be LT. Whenever you use small l, it will be LIM. Either you have to use like this or like this. These are the two conventions we will be using in limits and continuity. So this is how we will calculate the steady state error. Again, steady state error depends upon number 1, R of S. What is R of S? It is a reference input signal. And number 2, what is this? G of S into H of S. G of S into H of S is nothing but it is open loop transfer function. Steady state error depends upon these two parameters. Let us see an important topic in module 3, which is steady state characteristics. The same thing, we will recall what is steady state error. The steady state error depends upon the input signal and open loop transfer function. First, they have to specify what is the input in terms of S. Generally, what they will give in the examination is, instead of S domain, instead of input signal like ramp input, step input or parabolic input, they can give a function in terms of S, and you can obtain what are the steady state characteristics for that function. Let us see in detail what is the steady state characteristics. First, I will take the first signal, that is step input. Again, we need to recall what is the step input signal characteristics. The step input signal characteristics will be like this. It is having a step. This is a step. The signal will be jumping from lower level to higher level. This is O, this is T, and this time I will be writing this as C of T, controlled output signal. Step input, what is R of T? R of T will be equal to A into T. No, it's just A. It is just stepping. The magnitude only you will be writing 0 to A. What is R of S? If you apply Laplace transformation, R of S will be equal to A by S. The Laplace transformation of 1 is 1 by S, same thing. Let us see what is steady state error. Steady state error will be limit of S tends to 0, S into E of S. What is E of S? E of S will be equal to S into R of S divided by 1 plus G of S into H of S. I will be considering the step input. So limit of S tends to 0, S. What is R of S for step input? it is a by s into 1 plus g of s into h of s. S will get cancels, limit of s tends to 0, a divided by 1 plus g of s into h of s. This is steady state error for step input signal. In order to make an easier analysis, we will be introducing a proportionality constants. The first proportionality constant for step input is nothing but it is Kp. Kp is nothing but it is a proportionality constant for step input, which is called as positional error coefficients or static error coefficient. This is error coefficient corresponding to position or displacement error coefficient. There are several names. So Kp is proportionality constant. Why we have defined this is, if I apply limit of g of s h of s, we don't know what is g of s h of s, that will be given in the problem. So g of s h of s we have to derive. That's why what is limit of s tends to 0 g of s h of s. So for easier analysis I will be using Kp is a proportionality constant for step input. So Kp is limit of s tends to 0 g of s into h of s. So finally the steady state error will be equal to a divided by this one is constant 1 plus Kp. So this is a steady state error for step input. How the steady state error will be differing? This is an ideal input. So I will call it as desired output. But actually the output will not be like this. It will be somewhat like this. And then it will be constant. This is actual output. If you measure this difference is ESS. So this ESS will be 1A divided by 1 plus Kp. Let us take the second one. Second one is ramp input. The same thing graph we will be recalling it. Ramp input. This is T, this is C of T. And what is the variation? The variation is just like a ramp, it is varying linearly. This is desired output. And this is C of T versus T. Let us recall what is R of T for ramp input. It is A into T whenever T greater than or equal to 0. Here we will always consider T will be greater than 0 only. What is R of S? Apply Laplace transformation. R of S will be equal to A into Laplace transformation of T is n factorial divided by s to the power of n plus 1. Here n is equal to 1. So 1 factorial divided by s to the power of 1 plus 1, that is 2. Again, what is steady state error? Steady state error is nothing but it is limit of s tends to 0, s into E of s. Directly I will be writing what is E of s. E of s is R of s divided by 1 plus G of s into H of s. Substitute the values again. Limit of s tends to 0, s into what is R of s? A divided by s square divided by 1 plus G of s into H of s. S will get cancelled. Limit of s tends to 0, A divided by s into 1 plus G of s into H of s. Again there is a trouble. You have a s term in the denominator. When you substitute the s here, the value will be changing. Hence what I will do for simplification is I will be defining another proportionality constant similar to positional error coefficient. So this is Kv. Kv is nothing but it is velocity error coefficient. What is velocity error coefficient? Velocity error coefficient is nothing but limit of s tends to 0. Here there is a s term, s into g of s into h of s. This is the velocity error coefficient. Therefore, steady state error for ramp input will be equal to what happens? If I apply limits, a divided by s is also here, s into g of s is also here. So directly I will be replacing kV. So this is a steady state error for ramp input signal. So if I consider the actual output, it will be like this, and here it is a constant. This is a steady state error. Steady state error is nothing but a divided by kV, k suffix small v. So this is actual output. The last thing, what is parabolic input? Parabolic input, the same thing. First, write the characteristic graph, time versus controlled output signal. It is varies like a parabola. This is a desired output. Desired output means what we need like this. We need ideally like this. So what is the expression for parabolic input? A into t square by 2 if t is greater than or equal to 0, not equal to, greater than 0. Apply a Laplace transformation, same story. I want R of s here. R of s will be equal to, what is the Laplace transformation here? A 2 into 1, that will get cancels. A divided by s cube, directly I will be writing. And what is a steady state error? Steady state error is limit of s tends to 0, s into e of s. What is e of s? R of s divided by 1 plus g of s into h of s. So I will substitute the limits again. Limit of s tends to 0, s into a divided by s cube divided by 1 plus g of s into h of s. S square is the remaining, and that will be coming to the denominator, a divided by s square into 1 plus g of s into h of s. In order to make our life easy, again we will be defining another constant. That constant is proportionality constant for parabolic input. It is called as acceleration error coefficient. Sometimes derive an expression for static coefficients in the exam. If they ask, you have to derive these two. What is acceleration coefficient? Ka will be limit of s tends to 0, s square into g of s into h of s. This is the acceleration error coefficient. And if I substitute this, ESS will be equal to a divided by k into a. This is the acceleration error coefficient for parabolic input. So what is a steady state error? The output will be like this. This is steady state error. ESS will be equal to a divided by ka, and this is actual output. What we have done is, we have done only what is R of s. We have calculated R of s and replaced it. Then we got steady state error for unit step input or step input, ramp input, and parabolic input. If they ask unit step input, make a is equal to 1, that's all. If a is equal to 1, if a is equal to 1, you will get unit step or unit dash signal, I will write. If it is a step, unit step signal. If it is a parabolic, unit parabolic signal. If it is a ramp, unit ramp input. Let us recall the concept of static error coefficients. These are also called as proportionality constants for different types of input. The first one, it is positional error coefficient. Positional error coefficient, we will be getting this for a step input. So, Positional error coefficient is defined as Kp will be equal to limit of s tends to 0 g of s into h of s. So this is the proportionality constant for a step input, which is called as positional error coefficient. When we consider the steady state error will be A divided by 1 plus Kp. So if it is having an unit step input, A will be equal to 1, that will be equal to 1 divided by 1 plus Kp, and this is for unit step input where A is equal to 1. Similarly, the second thing is velocity error coefficient. Velocity error coefficient is for ramp input. So velocity error coefficient will be given by Kp. It will be limit of s tends to 0 s into g of s into h of s. This is the proportionality constant for ramp input, which is called as velocity error coefficient. The steady state error will be A divided by Kv. If it is a unit ramp input, it will be 1 divided by Kv, A equal to 1 because it is unit ramp input. After this, there is another error, that is acceleration error coefficient. Acceleration error coefficient is nothing but Ka limit of s tends to 0 s square into g of s h of s. This is acceleration error coefficient or proportionality constant for parabolic input, which is called as acceleration error coefficient. The steady state error for this system will be A divided by Ka, where Ka is acceleration error coefficient, and if it is having a unit parabolic input, A equal to 1 because it is unit parabolic input. So these are the things we derived. Why we have derived? Keeping this into consideration, we will be defining what is the steady state error for a different systems. So the different systems is segregated based on the open loop transfer function g of s, h of s. So two things we are taking here. One is R of s, because if I recall the basic convention of steady state error will be limit of s tends to 0 s R of s divided by 1 plus g of s into h of s. So this is the equation where R of s, what we have seen, these are obtained from these equations. We need to take care what is 1 plus g of s h of s. So that is 1 plus g of s h of s is depends upon the system. So k into 1 plus st1, 1 plus st2, etc. The numerator terms, then s to the power of n, 1 plus sta, 1 plus stb, etc. If you make characteristic equation is equal to 0, then you will get open loop transfer function as some equation. So this polynomial consists of numerator and denominator terms. The numerator terms, if I equate this as 0, that will be in the form of 0 by 0. 0 by 0 is nothing but an actual 0. If I make denominator as 0, then it will be 1 by 0. These are called as poles. It will be infinity. So these two are the important concepts here, and beyond which we will be worried about what is this n. N is, if n is equal to 0, n is equal to 1, and n is equal to 2. It indicates n is equal to 0 indicates s to the power of 0 is 1. That means there is no pole at origin. If you plot graph, this is S0, 1, minus 2 like that. If S is equal to 0 means there is a pole at origin. If there is no S term in the denominator, that means there is no pole at origin. N is equal to 1. N is equal to 1 indicates there is a S term. S term indicates S to the power of 0. There is a pole at origin. That means one pole at origin. N is equal to 2 indicates there is two pole at origin. Two poles at origin, plural. Whenever n is equal to 0, these systems are called as type 0 systems. If n is equal to 1, it is called as type 1 system. If n is equal to 2, it is called as type 2 systems. Whenever we deal with the type of the systems, we will be knowing what is the location of poles, whether there is a pole at origin or not. So these concepts are very important in order to analyze the steady state analysis for a certain system. If I take certain system, the certain system consists of an open loop transfer function having the terms in numerator and denominator. Mainly we will concentrate on s to the power of n, s to the power of n, where n represents the type of the system. There are s terms here also. If it is having s into s square plus 2s, suppose the example is if the term k into s plus 2 divided by s square, s plus 4, s plus 5. For this highest order, s square, s into s to the power of 4, the order will be equal to 4, the order of the differential equation, but which type of the system? In order to decide that what is the value of n, that means s is equal to 0 term should be there in order to define the type of the system. Here the type is 2. Another example, if we take example 2, k into s plus 5 divided by s square plus 4s plus 1 into s plus 2. What is the order here? S square plus s square into s. It is order 3, but what is the type of the system? Type of the system is 0 because there is no s term here. S to the power of 0 is 1. Like this, there are several cases. If we analyze these cases with respect to error coefficient, then the value of steady state error can be easily identified for the different type of system. So first I will take positional error coefficient. Positional error coefficient is Kp, limit of s tends to 0, g of s into h of s. So if I consider a type 0 system, positional error coefficient will be limit of s tends to 0. What is g of s, h of s for type 0? So k into 1 plus st1 etc. divided by s to the power of 0, 1 plus sta like that etc. If I solve the limit s to the power of 0 here, then I will get certain value. What is that value? Since there is no s term existing individually, 1 plus something, 1 plus something, so it will be 1, but remaining value will be k. So what is the steady state error? EASS is equal to a divided by 1 plus kp, it will be 1 divided by 1 plus k. This is the steady state error. This means there is some steady state error magnitude here. Next, if I consider a type 1 system, type 1 system, again Kp will be equal to limit of s tends to 0, k into 1 plus st1 etc. divided by type 1, n will be equal to 1 here, so 1 plus sta etc. If I solve this, since there is a s term here, if I give 0 here, what will be the value? Anything by 0 is infinity. You will get proportionality constant as an infinity, then steady state error 1 divided by 1 plus kp, 1 divided by 1 plus infinity. 1 plus infinity is again an infinity, 1 by infinity is 0. So here steady state error will be equal to 0. That means there is no error here, type 1 system. The steady state error will be 0. But what will be the value of proportionality constant? It will be infinity. So next, type 2 system, there is no type 2 system here because this itself is infinity. Again, that will be also infinity. We will stop only type 0 and type 1 system for positional error coefficient. If we take velocity error coefficient, again s into g of s into h of s, the same thing you will get multiplied with s, and again you have to see how many error coefficient will be exist. Let us see the same thing for velocity error coefficient. Second thing is velocity error coefficient. It is given by kv, limit of s tends to 0, s into g of s into h of s. And what is the steady state error? Steady state error ESS will be equal to A divided by kv. If I consider type 0 system, I will write directly kv will be equal to limit of s tends to 0, s into k into 1 plus st1, st2, etc. divided by s to the power of n. S to the power of n will be equal to 0 here, 1 plus sta, stb, etc. So if I apply limit here, what happens? This s will get dominated, it will be 0. So proportionality constant for velocity will be equal to 0 for type 0 system. Similarly, steady state error a by 0, what is a by 0? Infinity. So we need to avoid this system. Then if I consider type 1 system, kv will be equal to limit of s tends to 0, s into type 1 system, n is equal to, here n is equal to 0, n is equal to 1, k into 1 plus st1, etc. divided by s to the power of 1, 1 plus sta, etc. ss will get cancels, kv will be equal to k, therefore steady state error will be equal to a by k. Then again we can go for type 2 system also. Type 2 system n is equal to 2, k suffix v will be equal to limit of s tends to 0, s into k into 1 plus st1, 1 plus st2, etc. divided by s square 1 plus sta, etc. etc. ss will get cancels, 1s is in remaining. Because of that, kv, if you apply limit s to 0, it will be 0, 1 by 0 is infinity. What is the steady state error? A by 0, sorry, a by infinity, it will be 0. Next, here steady state error does not exist, further is not used, hence for velocity error coefficient we will be stopping at type 2 system only. Next, number 3, acceleration error coefficient. In acceleration error coefficient, Ka will be equal to limit of s tends to 0, s square into g of s into h of s, but steady state error will be a divided by Ka. Again, for type 0 system, n is equal to 0. If n is equal to 0, Ka will be equal to limit of s tends to 0 s square into k into 1 plus st1, 1 plus st2, etc. divided by s to the power of 0, 1 plus sta, stb, etc. Since there is a s square, if s is equal to 0, this ka will be equal to 0. What is the steady state error? A divided by 0, it is infinite. Next, type 1 system. Type 1 system, n is equal to 1. If n is equal to 1, Ka will be equal to limit of s tends to 0, s square, same story, 1 plus st1, etc. But here n will be equal to 1, that's why it is s, 1 plus sta, stb, etc. So 1s will cancel, again still there is a s in the numerator, because of which Ka will be equal to 0, steady state error will be equal to infinity. Directly I am writing. Next, type 2 system, n is equal to 2, Ka will be equal to limit of s tends to 0, s square, k into 1 plus st1, etc. divided by s square, 1 plus sta, etc. So s square will get cancels. If you apply the limit, only the constant will be existing. So steady state error will be equal to a by k. Next, the last system is type 3 system. Type 3 system, n is equal to 3. Ka will be equal to limit of s tends to 0, s square, k into 1 plus st1, 1 plus st2, etc. divided by s cube, 1 plus sta, etc. If you apply limit, what happens? The value of Ka will be equal to anything by 0 is infinity. And what is the value of ESS? ESS will be equal to 0. That means up to type 3 system, the acceleration error coefficient will be appearing. For type 3, it will be 0. So here you have to identify. If you consider acceleration error coefficient, up to type 3 system, you can work. If you are using velocity error coefficient, up to type 2 system. If you are using positional error coefficient, up to type 1. So various proportionality constant will give you what is the steady state error. By making use of steady state error, you can adjust, you can make the system to be stable. So this is the steady state analysis for different kinds of input. Here there are two things. One is R of S, that depends upon the input type, and another one is open loop transfer function. Open loop transfer function is just a pole at origin, that is type 0, type 1, type 2 systems. That's all.